So heat and energy are really important for us to review. It's easy to get heat mixed up with temperature, right? Heat is the transfer of energy because of a difference in temperature. And it's always from a higher temperature, heat always goes from a higher temperature to lower temperature. So, you know, temperature is directly related to the average kinetic energy of a substance. So if you have water that's at 75 degrees Celsius, pretty well on its way to boiling, those they're moving around pretty quick, right? But if you have 10-degree water, those particles aren't moving around very quick. But if you put those together, the molecules inside here are going to be moving quick and banging into these, and then these will start to move faster. And then eventually those will reach the same temperature and be in thermal equilibrium. So we use this illustration back in our original unit where you've got the can, and the molecules inside the can are moving quick, and then it hits the metal atoms, which move quickly, and then the slower water molecules that are at 5 degrees start to move faster, and then eventually you reach thermal equilibrium where both are at the same temperature. Transfer by heat transfer by touch is conduction, right? So this is molecules banging into another, and convection is the movement of molecules, mass movement of molecules from one place to the other, and we see this in heating up water, or the thermal system of the water going through, or air moving through a building. And and so we see that with convection. And then radiation is where we're looking at the electromagnetic rays that are shaking the molecules, making those go faster. And so now this should make a little bit more sense, because we spent all that time in electromagnetic radiation looking at how light affects things. And so light will heat objects up, shaking those molecules. Okay, so specific heat capacity is another important definition. It's the amount of energy required to change the temperature of 1 kilogram by 1 degree Celsius. So let's say we have 1 kilogram of water, which is about a liter, and we put heat into this water, and it goes up by 1 degree Celsius. For water, it's going to take 4,186 joules to do that. And so that water will heat up by 1 degree Celsius. And different objects have different specific heat capacities. For instance, lead, which, let's illustrate that here. So let's say we have 1 kilogram of lead. It only takes about 130 joules to heat that up. Now, what's kind of interesting is, let's say you had both of those and you heated, I don't know, let's say we heat them both up by 3 degrees Celsius. So we heated this up by 3 degrees, heated this up by 3 degrees. Well, that's going to be quite a bit of energy that's going to take to heat up this water. For to heat up this by 3 degrees, it's only going to take 3 times this, which would be what, 390 joules to heat this up. So this is going to absorb a lot more heat for 3 degrees than this one will. And so therefore, if you leave them out, is sitting outside, this one, this has a lot more energy in it. It has a lot more thermal energy. So specific heat is directly related to that. I think it's important to emphasize that here. Many different, types of objects here, they all have different specific heat capacities. So let's practice this one as a first one here. How much heat does it take to raise the temperature of 1 kilogram of aluminum by 2 degrees Celsius? So get your counting equation sheet and your calculator. Go ahead and give this a try. And when you're ready to check, you can hit play to continue. All right, so it should get 1,800 joules. On your equation sheet, it has it as MC delta T. And, this is just rearranged. And, same equation there. Let's go ahead and practice this one. This is a little bit more involved. This one, last one you probably could have done just using logic. This one you'll need to work out. How much heat would it take to raise 1.5 kilograms of copper from 19 degrees to 25 degrees Celsius? So yeah, go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right. So for this one, we should get 3,510 joules. And we know the mass, we know the temperature change, we know the specific heat of copper. And again, on your equation sheet, it looks like this, MC delta T. All right, so if you remember back in this unit, we looked at how, we can figure out what different objects are based on their specific heat. So let's say we have a rock that we find and we heat it up and then we place it into the water. Eventually, those are going to reach thermal equilibrium, right? So heat out of the one will be equal to heat into the other. And let's practice this one here. We have a 100-gram rock. So the mass of this is 100 grams, which we can convert to kilograms, 0.1 kilograms. And then the initial temperature is 75 degrees Celsius. And we have this, we're going to place it into water. And the mass of the water is 0.5 kilograms. The specific heat of water we already know, 4186 joules per kilogram degrees Celsius. The initial temperature of the water is 10 degrees Celsius. And eventually, after we place this mass into the water, the final temperature will come out to be 10.398 degrees Celsius. So the question is, what is the specific heat of the rock? Now, if you look on your equation sheet for calorimetry, we have mc delta T equals negative mc delta T. And what we have to remember is that on the right-hand side, this is what we want to use for the object that is losing energy. And so that turns out to be this. This one's the one that's losing energy. And we can find out what the specific heat capacity is. So yeah, go ahead and pause the clip and calculate what the specific heat is. And when you're ready to check, you can hit play to continue. All right, so we should get an equilibrium temperature of 10.398, and then we can solve for the specific heat, and we'll get 128.95 joules per kilogram degrees Celsius, which is very close to lead. And so, there could be experimental error in these labs, or these experiments, and we saw that when we did this lab ourselves, back in this unit. And so that's a very, real fact of this here. All right, so on this one here, we're going to mix 2 containers of water. We can write out the variables here. We have this water here, mass 1, 2 kilograms, it's at 15 degrees, and then we have the other one, which is 75 degrees Celsius water, and we're going to pour this one into this one, and we want to find the final temperature. And so again, we use specific heat capacity, or really the calorimetry equation, mc delta T. Now the question here is, and then try to get this better here, M, there you go. This one has to be the one that's going to lose energy, which if we look at it, that's going to be this one. This one's going to be losing the energy. So yeah, go ahead and give this a try and calculate out the final temperature. And when you're ready to check, you can hit play to continue. All right, so the best thing to do here is just make sure you write out each step. We've got these being multiplied, then we distribute in, and we add up our like variables together. We should get 57.245 degrees Celsius is the final temperature of the combination there. And so yeah, it's important, I think, to get practice with that. I mean, this is kind of practical, right? If you're mixing 2 things, these could be chemicals, different liquid chemicals, and we want to know the final temperature, and we can control that by the initial temperatures.